Hello there everyone, welcome for a short digression. My name is Ludovic Lagouardette and I'll be presenting you this short digression starting with x86 addition. x86 addition, the tippity top of the rabbit hole of a modern CPU. So this is C or C++ or whatever typical programming language you may use. If we compile it with a modern compiler, we will get something like this. This is going too far. We are gonna go back to an old compiler without optimization. So this addition function does a lot of extra work. It sets up the stack properly and then it performs the addition before destroying that stack and returning. That's a lot of extra work. But we may have a way around it. Note that it also has to do a lot of moves. So this is what we would like it to look like, but we cannot just remove the setup. We need to extract the two arguments, which happen to be in EDI and ESI. So let's go back to the optimized version. We do nothing to the stack. The stack is untouched. We just get the address with the value that is the sum of RDI and RSI. It could be EDI or an ESI, but we must use the long registers because we are on x86 64. And this is very efficient. It uses the very same addition machinery as add, but we don't move anything and we just use the LEA instruction, which is a load. And then we exit the routine, stack cleanup with the ret, everything's done. So what is that addition machinery we're talking about? Here you have an adder, takes two inputs, A and B, and returns an output, S. And it also takes a carry, in case we have another adder, and it outputs a carry, in case we have another adder after it. So this is a 4-bit cascade adder. We take the inputs and we cascade them around. So this way we can addition 4 bits, and you can imagine expanding that for 32 bits. But for each adder we add, you notice that it depends on the adder before it. So it adds a little bit of delay. And that delay, speed of light, pretty large value, but it can be summed up by saying that it's 30 centimeter, roughly 1 foot per nanosecond. And a CPU frequency is 3.0 gigahertz, which is 3.0 billion instances per second. So that means that in a cycle, light can move about 10 centimeters worth of circuitry. And light is not as fast, is not as slow as electricity. Electricity is twice as slow. And remember, like, it's not 10 centimeters in a straight line. It's 10 centimeters of total instructions. And each instruction is made of a bunch of discrete microcodes which compose the instruction. But wait, what are those microcodes? Well, the CPU industry got problems to solve. The speed of light, as we saw, is very annoying. The die space is very expensive. And stuff being away from memory, like your memory being physically at a certain distance from whatever is doing your computations, is also terrible. And the main solution is reuse die space, and reuse die space some more, and make some more primitive CPU emulate the actual CPU, and that's what microcodes are about. So this CPU executes a microcode program for every instruction. So an instruction, like add or LEA, is made of several microcodes. And now we can decouple the instructions and what they are doing. So we can make complex instructions with several steps and reuse machinery of the CPU. And this allows us to also execute this instruction partially in parallel so that they can overlap slightly. So this also means we can update our CPU working process. So we saw it with the Spectre meltdown issues. Some CPU could get some microcodes update to, well, work around that all. So let's say an hypothetical CPU may implement those LEA and ret instruction to make things faster. So first of all, we need to load the data to perform the LEA. So we can load that data and start engaging the return immediately, because we do not touch anything else except EAX. And return doesn't touch EAX. Like return the ret, it will alter the stack structure and the stack pointer, never touching EAX. So ret doesn't need the other machinery either. LEA needs it, but ret doesn't. So before LEA is done, we can already return. Return doesn't actually write to any register, like I said, neither RDI nor RSI. But if it did, it could wait until the data is read to execute. And if ret actually wrote to EAX, we would have two situations. Either we interrupt LEA because EAX would be discarded, like the result of the LEA would be discarded. So we can interrupt it. We are not doing actually anything, so we can ignore it. Or we can wait for the LEA to finish, which is actually what most CPU would be doing. So now that we've done that, let's go up the stack. Anyone knows what this is? This is what generates an integer addition in the beam, the virtual machine about Erlang. Hi, you thought I was gonna do a talk without talking about Erlang? So this function is rather simple. It makes a label in case things would fail. So you get two labels here. So we will read the two arguments, the left-hand side, the right-hand side. We look if they are small enough, because if they are not small enough, you cannot do 32-bit addition on them, because the Erlang beam has big integers. And so you have a comment inserted in there to say that we are adding with overflow check. We are moving a few values, and more importantly, we are marking the result of our addition as an immediate value, because if you add two 32-bit integers, you know that if you add them with overflow check, you're never gonna get something that's not a 32-bit integer. And we perform the addition, and we jump to what's supposed to happen next. And after that, we will return the value directly. So what else could happen is if we have mixed integers, then we actually need to perform either a long division, a long addition, or any other form of addition. So we have a function to do that. And if we are not given a fail-safe, so something to execute if we fail, which is actually a jump, so a label, we actually must perform the unguarded addition because we have no way to handle the failure. And then we go back to what we expected, so returning. So what have we seen today? We have learned that optimization is subtle. CPUs are very confusing. They have a lot of tiny mechanisms that are made so that they respect the laws of physics. And your programming language should respect the law of physics. And your computer may use trickery to actually do that, like levels of cache and stuff like that. So code sharing happens at all levels of the architecture. LEA shares code with addition in your CPU in hardware. Just like this addition in hardware is repercuted into the beam by its code generator. And even your JIT is more often than not, your JIT or your interpreter is more often than not just an abstraction on top of those abstractions. So this digression is finished. You can hit me on Discord or on Telegram as seen up there. You can check out my blog or hit me by email. I offer some programming courses, mainly in C and C++. And have a great day.